So this is about the reasonable performance computing special interest group knowledge base. Last year, following our SIG-RPC 24, there was a positive reaction to my talk about performant Python patterns. So we set up a small special interest group to try and gather more of these kinds of patterns. And this is hopefully a workshop where you can contribute some of your own ideas and experience, because I'm very much a specialist who works with C++, Python, but I don't touch data tables, I don't touch R, I don't touch MATLAB, Fortran. All of you have very different experience, very different domains, where there's got to be lots of different performance patterns that no one person is going to know all of them. So we're trying to gather all of these ideas. So what is the right tool for the job? When a researcher looks at code, if they've not got that computer science background, which the vast majority of them do not have, they can be looking at this like someone who's not a manual labourer and go, what is the right drill for my job? I was installing a Ring doorbell for my old Gemini neighbour about a month back, and they kept thrusting me a wood drill. When, yeah, you need to use a mason drill and hammer. We did not have it on hammer, and it caused problems. So it's kind of, you need to think of it like this when researchers are looking at code. They might know what to do something, but they do not know the right way to do it. The typical researcher, they're a domain expert. They really know their field, which might be microbiology, it might be physics, but they're not necessarily a strong programmer. They're probably self-taught, and this means they will have picked up bad habits. And they're also short of time. We know all researchers, they've got a lot of pressures on them, writing papers, writing grants, well, not all of them writing, but writing grants and stuff. So they haven't got all that time to go and do like a full computer science degree worth of learning about algorithms, data structures, and just lots of experience programming. And they're also just picking up inherited code. And this has typically been developed by more researchers who have got exactly the same pattern of domain expert and self-taught programmers. So it's how can we work around these bad habits to catch these things. For some reason, that's cutting something off the edge of the slide, but no. So this leads to coding traps. These are things that are often unnoticed in code, and many of them have been used for years, because a lot of code is inherited, as I've just said before. And we can find many common traps between different projects, different languages. This one on the right-hand side, this is the most common that I come across, at least, where we have people who are basically managing uniques with an array or a vector, just doing linear searches over and over through an array or a list. If they swap back to a set, they'll often get speed ups that can be as high as 1,000 times if they're working with like millions of data points, which they quite often are. So this is what we're kind of considering unreasonable performance. This is something that if you profile this, it's going to come out and be like, oh, look, 80% of your runtime is in this method that's doing this. Doing this. And kind of, if you know what you're looking at, you go straight away, yeah, this should be using a set. You can make that change really quickly, and you can get them that massive improvement to performance. We're not looking at advanced, like really highly technical optimizations. It's looking for these really low-hanging fruit that we can hit. So a recent case study, 26th of August, about 3 weeks ago, a project I was actually working on for, I think, 6 months last year or earlier in the year. They actually said, can we actually profile the code because we've got nothing else for you to do, and they've got some spare money. It's a C++ and OpenMP project, and development began in 2010, and since then it's had 9 authors, a mix of PhD students and postdoc research associates. So this is very typical research software which has been used for years and been inherited and moved through authors, and it's now got 12 publications, so very representative. So one of their current users, who is not a developer of the software, was told, please give him a copy of what you're running, what you're testing, because I think they're trialing the software to see whether it will work for their biological stuff. So I know nothing about finite element analysis. The software is a bit of a mess. We had a paper, better architecture, better research, about how bad the software architecture is. So this is basically a simulation of a bundle of rods. I don't know what rods are. It's something to do with modeling very small cells. And you run the simulation with this kind of command here, FFEA, and you pass in the input file. This took 312 seconds, because again, it's a very small test they're using. But to profile this, we basically run it through gprof, which because we've configured the CMake properly, we just pass these extra things to basically set the PG flag to all of the levels of the profiler. And we also disable OpenMP, because gprof, OpenMP, you kind of get some spurious data you don't like. And you rebuild it with CMake, as we do here. That's what we do to set up gprof. And then to profile it, we run it exactly the same as before. And that spits out a file, gmod.out, which you then pass through gprof, and it will generate your output. So I did that. And what we see here is kind of suspicious. Like, is anyone seeing the problem? So we've kind of got there. 54% of the runtime is a copy constructor of an object called rod. 20% of the runtime is a vector copy constructor, and 11% of the runtime is the destructor for the class called rod. So like, that's a huge part of the runtime, just copying an object which seems suspicious for something which is simulating what looked about 500 rods. So I open up the code, well, the file which contains rod, and we can see we've got this really complex class which contains 30 scalars, 28 vectors, and 3 strings. So like a big complex class, it's not a small struct that we're copying. And that kind of explains where the copy of vectors was coming from. And then we look down to the methods on this class, and we can see that every single method returns an instance of rod. And we go one further and actually look at the implementation, and we find this comment, return a pointer to the object itself instead of void, allows for method chaining. Not quite right. They're returning a copy, so you can't actually chain it, and they're not returning a reference or a pointer. So to fix this, we just replace all the returns with void and get rid of them, because no one was chaining. Chaining didn't work. We reload it with gprof disabled, OpenMP enabled, and rerun the code. And it runs in 31 seconds. That's a 10 times speed up with an hour's worth. This is kind of the unreasonable performance that we're trying to highlight and raise awareness of among researchers and help them try and solve and identify themselves, or with the support of RSEs. So this mistake was first introduced in 2018, 8 years after the code started being developed, but still 8 years ago. Well, 7.5 years later. It took about an hour's work, a bit longer to work out how to run the example, because whatever, they've got an issue with the code that when you run it, it creates corrupted output files that overwrite the input files. So you have to generate new input files. So like, it took me longer to get it to run it than to actually fix this. And this is central to all simulations using rods. The code base has blobs and rods which it simulates, so it's about 50% of the code base. So we can assume a broad, similar 10% speed, 10 times speed up to everything that touches rods. A recent PhD graduate, they heavily used the rod code, like it was their project, looking at the rod simulations. They did not implement this. That was the person before them. And I kind of discussed the performance with them, and they kind of gave me this pseudo quote from that part of their thesis. So considering the full range of 1 to 512 rods, they took from 3 minutes to 12 hours to run. So we're thinking about what is the impact of reducing a 12-hour run down to less than 2 hours. It's a significant speed up that, had someone done this when the code was originally produced 7 years ago, that's a lot of time that would have been saved on that person's PhD, increased productivity. They could have perhaps done more. And then also some people are concerned about sustainability. But there's all of these benefits, and this is all going overlooked because we do not talk about performance in research software written by researchers. We have a lot of emphasis on fair, findable, accessible, interoperable, reproducible, reusable, but very little emphasis on performance. My assumption at this stage is that a lot of that's because a lot of fair skills are soft skills that can be taught to beginners, but performance, you can't really start talking about profiling and optimizing until someone's comfortable with the language. And it's very difficult to target that training, whereas targeting fair stuff, we generally get it to beginners. So it came to, how can we start enabling researchers to catch and address these similar problems? And that's where the knowledge base came in. So first we developed this training. Well, I developed it about 2 years ago, and Yost is now helping co-maintain it. It's now in beta status on Carpentries Incubator, and it's been run at several universities. But training, it doesn't really scale very well. It took a month to develop that course, and it's had even more time from myself and Yost to get it up to this beta stage. So we cannot afford to do this for every niche like Python library or niche language. Like, we stopped teaching C++ as a short course for researchers and staff at the University of Sheffield because there wasn't the demand for it. But we know from examples of this project, there are people writing C++ and using C++. So it's not possible to create bespoke Carpentries short courses for every possible niche use or combination of languages and libraries that people are using. So the goal is to move to this knowledge base. So I think Christmas last year, I put together this website. It's a static website built on top of Jekyll, and it essentially holds this knowledge base for mini guides, really short, compact guides on how to do hot path profiling with profilers. There is coverage of other profilers, but the emphasis is largely on hot path profiling because that's where you find these things. And then identifying the performance patterns. Because again, as I've said before, a lot of these are very common mistakes. Like that one there is doing redundant copies. A lot of the thing will be redundant stuff. We will have just issues with data structures, algorithms, and just finding the better ones to do. So in theory, this stuff should be quick to write and easy to understand. It's trying to minimize the cost of people actually putting together this guidance and people consuming it. So that's largely what the workshop here today is for. So a profiler guide, this is just part of the search directory, but you should have scattered on your tables some example. Well, I think I printed off one of each of the profiler and optimization guides we currently have. So I don't know which you will have on your table, but they're all unique. So profiling, we filter them by language and style. Style largely being like function profiling, line level, memory, hardware metrics, timeline, or you can add other stuff if you really want to. And then within that, we have simple stuff such as quick start, simply how do you profile your code, interpreting the output that you get from that, and then limitations of the profiler. This is mostly related to things such as multi-threading, because we will find stuff like OpenMP. This profiler doesn't really support parallel. As I said before, like gprof, I've seen some very spurious outputs when profiling stuff with gprof. Profiling multi-threaded code with gprof. And then optimizations, they're filtered by language and subcategory. Most stuff at the moment is in core because they're core to the language, but in stuff like Python, we might have, say, NumPy subcategory because there's a lot of very NumPy-specific optimizations. And then within these, we simply have the sections description, like a high-level summary of what the problem is. It's like an abstract. An example benchmarks, a simple way to show good versus bad, and then maybe some technical detail if you understand that. And it could be there for people who are more interested in this. It's not really necessary to understand the problem, but it can help explain it and embed the knowledge for people who are reading about it. So yeah, the website, it's built on Jekyll. It's very easy to maintain. You just write these very simple guides in Markdown with the YAML header. And you just have to include this more chevron thing to basically say, where is the fold in the content? So when I go back to this page, like the fold, anything, the more would be placed after that functions paragraph. So it would mean you do not get more of that body printed in the page. So that's basically all you need to know to contribute to this. So we've got 3 tasks set out. 1, reviewing. Myself and the people who have contributed these insights, we're highly technical people. So if you're sitting there uncomfortable, I don't really know something that I can put forward, I don't know enough about this to contribute something, please look at existing content. Does this make sense to you? How can we kind of improve the detail and make it something that's easy to read and understand and actually use? Because ideally, this should be something we can give to researchers and like researchers who are self-trained programmers and do not have that high technical experience. So it's trying to make sure we can keep these accessible. And likewise, if you're an expert, or say a certain profiler, what details are missing? Is there any important stuff that we can improve on that? So most of the stuff we're doing here, if you've got your laptop, please create a GitHub issue, or if you've not got a laptop, fill in a paper form. I think there's a large amount printed, but I don't know if we'll have enough. But we can go and rob some more paper if not. If you need pens, I have a lot of SIG-RPC pens I borrowed. So the next task, yes.
That's a quick question. So I don't want to talk before. I had a question. Now you looked at how many of these code fragments and things like that, but if people just put their code into Copilot or something like that, it would suggest the right optimization that you suggest on your.
That isn't something I've done yet. So the question was, have we used Copilot to look at identifying some of the optimizations? I'm aware that there's a profiler, I think, Scalene, which was developed at a university in the US for Python. That does have the ability to connect OpenAI keys, which is supposed to then use AI to try and suggest optimizations, but it's not something we've got to yet.
Because it might be that, I know a lot of people, you're saying a lot of people don't go look at it, that might be the thing they do now, is go put the code fragments in and go optimize them.
Yeah. But again, we still need to get we need to get them profiling first. We can get to the code fragment. But again, it's gathering these because then maybe we can start training something specifically on real world examples is part of the problem. So then editing. So again, that's kind of building on the review. If you've got the understanding and know how to improve something, put forward suggestions. We need to make this as wide as possible. And then finally, creation. So you can draft on guide. As I've said, like they're all very short. Most of the optimization guides, they're less than like 2 sides of paper. The profiler ones are typically a bit bigger, but that's because they include images or outputs from the profiler itself. So again, submit a pull request or complete a paper form, or even just put something in an issue. Perfect is the enemy of good here. If we can at least draft stuff, we can then take the time to finalize things where other people have put forward ideas that we can just clean up and publish. I think that's the last of the slides. Yeah, so if you browse to our website, there is a link to the SIG-RPC blog post, well, somewhere on there, and that links again to a shared document which has a list of existing guides, because we have a link of the existing guides and a list of backlogged ideas that we haven't got around to publishing, or we know there should be stuff there, but we don't have the experience to do it. And it's also worth noting that the SIG-RPC AGM is scheduled for the 16th of October. Again, you'll find an event on the right-hand side of the website. Please do get involved. We need more ideas and energy to work out how we can grow this more. So I will move over to Slido to see if there's any questions before we try and get started. Okay, cool. I guess I will keep an eye on Slido. But if people want to kind of wave us down, there's myself, Peter, and Yost available if people have questions. Thank you. So Frank has put this question: have you tried analysing code performance of code in JOS to find pitfalls in code and patterns like that? So that's a decent idea. An extra slide that I had and didn't show yet. A university, well, an undergraduate research project that I'm running this year. We are planning to do this with research software at the University of Sheffield. So we have an undergraduate module within the School of Computer Science where 4th-year undergrads will work as teams to basically put together the research and essentially write a research paper. A small amount actually get published. So the idea of this research will be that we will have, I think they're now about teams of 6 students, consult with researchers across the University of Sheffield to review the performance of their code. It should be interesting to try and do a systematic review of within Sheffield to see where are these performance issues. Do they lie specifically with people working with C and Python and everyone using MATLAB is great at performance? Who knows? And is it in just particular domains where people are trying a lot more without asking for help? So that is a goal of something I'm hopefully working on this year and may have something to present next year. So thank you for your contributions. We're coming up to the end of the session. Please do go on the website, join our mailing list, and get involved by coming to our AGM and giving us more ideas of how we can bring this stuff forward. Thank you.